Hello, hello, welcome to our third lecture of linear algebra. Today we are gonna continue with the study of lines, but now in the three-dimensional space in R3, and in this case we can talk also about planes. Remember that what we are doing here is developing some intuition. This is not exactly a content that we cover traditionally in a linear algebra course, but I want to make a lot of emphasis on the geometrical aspects of linear algebra, and that's the reason why I'm including this topic in the course. All right? So remember that in our last class, we deduced a couple of equations for the line in R2. The line in R2. So we have a parametric equation. And for the parametric equation, what we need is a point at 0, y0, and a vector AB that is parallel to the line. And the equation is x equal to x0 plus a times alpha, y equals to y0 plus b times alpha, where alpha is real. But indeed, I'm using a little bit of the language because we have a couple of equations here, but well, I can write this in a vectorial form this way. I can put the alpha wherever we want. All right? And also a normal equation. And a normal equation, again, what we need is one point. I'm going to continue using x0, y0, and a vector, but now that is orthogonal to the line. Let me use here a vector P, comma Q, orthogonal to the line. Okay? And the equation is P times x minus x0 plus q times y minus y0 equal to 0. All right? Okay, good. So we are going to do the same now, but for lines in the three-dimensional space. All right? Before doing that, let me give you another example in R2, just a little bit more complicated. So notice that there are two things here. This is the information that we need to get this equation. This is the information that we need to get this equation, but at the same time, if we have the equation, this is the basic information that we can extract from the equation. Is it okay? That maybe we need to use it in a different way. There are two kinds of exercises that I'm going to be giving to you here. So now we are going to have very simple exercises. Okay? In which the information that you need, simple exercises, are those in which the information that you need to get the equation is explicitly given or provided, all right? And a little bit more complex exercises in which the information that you need to get the equation to solve the problem is gonna be implicit. So I'm not providing exactly what you need. I'm providing information that you can use somehow to get what you need. But you need to work a little bit more. Okay, so the information that you need Let me put an example of each problem here, each kind of problem. So, simple one. Find the normal equation of the line passing across the point 3, -2, and parallel and orthogonal to the vector -1, 4. Is that okay? So you say, to solve this problem, say normal equation. What do I need to get a normal equation? A point, or I have it here, and a vector that is orthogonal to a line, or I have it here, orthogonal vector. Okay? So what you need to get this equation is exactly what I'm providing you with. Is that okay? So this is pretty easy. This is the point, so this is at 0, y0, and this is the orthogonal vector, so this is P and this is Q. The only thing that you need to do is to plug these values here on the generic expression of your equation, which is giving us -1 times x -3 plus Q, that is 4, times y -2 equal to 0. Oh, well. Now if you want, you can distribute these values and combine the like terms and solve for whichever variable you want, depending on which are your objective. Oh, well. This is the solution basically of this problem. So this is a very simple exercise. But I can give you something a little bit more complicated. I'm gonna write it here. Oh, find the parametric equation of the line L if you know. I'm gonna give you the intersection point of the lines R and S is on L, where R is described by the equation, I'm gonna put it this way, -3 plus S, comma, 2, well, let me put it this way, -3 plus alpha, comma, 2 minus alpha, where alpha is a real number, and S is described by the equation 2 plus alpha, comma, 1 plus 3 alpha. And again, alpha is a real number. Okay, erase this part. This is the first information that you have. And notice that again, this is giving us information about a point on L, but it's not explicitly given. So this is providing us with information on one point on the line L, but we need to work to indeed have the two coordinates of that point. And the second part, well, with 1 point, we cannot solve this problem, so we need something else. And the second part is L is orthogonal to the line M described by the equation I'm going to put it this way, x equal to 2 plus 4 alpha, y is equal to minus 1 minus alpha real. Okay. And this second part is giving us information about an orthogonal direction to L. But again, we don't have explicitly a vector that is orthogonal to L. So somehow we are gonna be able to get a vector here that is gonna be orthogonal to L. And if we have a vector that is orthogonal to L, we are gonna be also able to get a vector that is parallel to L. That is what we need. But again, you say, oh, we are trying to get the parametric equation of the line. We need a point and a parallel vector, and we have information about that point, something that we can use to get that point, but that point is not, like in this case, explicitly given. And we need a parallel vector, so we have information about the vector here that is related to our line, that we are going to be able to get the parallel vector that we need, but that vector is not explicitly given. So that's the difference between the two kind of exercises that we are going to have here. Okay? Very simple ones and a little bit more complex. Obviously, the level of difficulty here can vary. How can we solve this problem here? All right. So first, well, we need to discover our point, and then we need to discover our parallel vector. How can we get the point? Well, what we have is the following. What is this telling us? Well, we have a line R, and we have a line S, and these two lines have an intersection point. And what we know is that L is passing across that intersection point. So if we want to know this point, we need to get the intersection point of these two lines. Is that okay? Is that good? All right. So obviously I'm not, these graphs here are not very accurate because I'm not using any specific value. I'm just illustrating what is happening. Okay? Okay. Well, notice the following. Look at the equation that I'm putting for R, the way that I'm writing the equation. Well, obviously, this equation can be rewritten as x is equal to minus 3 plus alpha, and y is equal to 2 minus alpha, with alpha real. And same thing for the second equation. So the second equation can be written as x equals to 2 plus alpha, and y equals to 1 plus 3 alpha, with alpha real. Is that okay? If a point is on the first line, the first lines are, that means that that point, for that point xy, we are going to be able to find a value of alpha satisfying, making these two equations, converting these two equations into identities. And the same here. So if x is on the line R, we are going to find alpha satisfying these two equations. If that point is also on the line S, that point, for that point, we are going to be able to find alpha, making these two equations, converting these two equations into identities. Is that okay? But if that point satisfies this and that point satisfies this, well, we are going to have that minus 3 plus alpha, that is going to be equal to the edge of that point, needs to be equals to 2 plus alpha, because it's the same thing, it's the edge, the same edge for that point. And the same for y. If y satisfies this, for some alpha, and y satisfies this, we are going to have this. Okay, and this is basically the first idea. But there is a problem with this idea. The problem that we have with this idea is that alpha is the standard notation that we are using for the parameter in a parametric equation of a line. So I'm using alpha for both parametric equations just because I'm using the standard notation. But the value of alpha that I need to get that point in R is not necessarily the same value of alpha that I need to get the same point on S. So this is not correct because if I'm use the same symbol for alpha here, what I'm assuming is that the value of alpha that I need to get that point on S is the same value of alpha that I need to get that point on R. And remember, what is the interpretation that we did to that? What is alpha? What is the interpretation of alpha? So look what is happening. I have my two lines, but this is the given point in, for the line R. And let's say that this is the given vector. Is that okay? All right? Let me put it this way. Again, I'm not too precise. I'm just explaining the idea behind this, the intuition behind this. But let's say now that this is the given point for S. So this is S, this is R. And now this is the given vector, the given parallel vector. So if we look at this, what is the interpretation of alpha? Alpha is how many times we need to repeat this vector to reach the point xy from the given point at 0, y0. So according to, let's suppose that the space that I have here is exactly the magnitude of the given vector. So in this case, the value of alpha that I need to reach the point, the intersection point, from the point x0, y0 on R is alpha equals 2. However, if we move to S now, from this point to reach the intersection point from this point using this given vector, let's say that this distance here is exactly the magnitude of the vector, but in this case alpha is going to be -1. Is that okay? So you see, even though the point is common to both lines, the values of alpha that we need is not necessarily the same. So if we set up this system this way to find the intersection point using the same symbol, so we can conclude that there is no intersection point because this is forcing the value of alpha to be the same for both lines, and that's not necessarily the case. Is that okay? So how can we fix that? Well, that we are going to keep alpha for one of the lines, and we are going to change the symbol just to allow these values to be different. That is the general situation that we have. And we can use, for example, beta. Is that okay? And now, this is basically leading us to a 2x2 system. We can rewrite it this way. Alpha minus beta. So this beta is positive, comes to this side negative. 2, this 3 goes positive to this -3 goes positive to the side, so equals 5. And here minus alpha minus 3 betas equals to -1. Is that okay? Well, basically, if we add the two equations, we are going to have minus 4 beta equals to 4. Beta is equal to -1. Is that okay? And, well, if beta is -1, alpha is going to be 4. Okay? If beta is -1, this becomes alpha minus -1 is alpha plus 1 equals 5. Alpha needs to be 4. Yes or no? Now you say, but this is not the point. This is not the point that we're looking for. To get the point, we need to come back to any of the two equations. Now, we are using alpha for the first one, and we are using beta for the second one. Both equations need to give us the same point. Okay, if I put beta, because remember that we changed the symbol. Beta equals -1, what we are going to get here? This is giving us that x is going to be positive 1, beta equals negative 1 is giving us that y is equal to negative 2. So the point is 1, negative 2, the intersection point. Well, this one needs to provide us with the same point. So if alpha is now 4, minus 3 plus 4 is giving us x equal 1. Alpha is 4, so 2 minus 4 gives us y equals negative 2. Again, the intersection point is 1, negative 2. Why? Because what is this value? This is, if you want, how many times we need to repeat the vector 1, negative 1 from the origin in my line, that is the given point, to reach this intersection point. And this is the time that we need, or how many times we need to repeat the vector 1, 3 from 2, 1, okay, to reach the intersection point 1, negative 2. The intersection point is 1, negative 2. So now this abstract information has been translated into what we want. That is the point, 1 point on the line. So out of the two things that we need, we have the first one. We have the point now. Okay? What do we do to get the vector now? How do we do to get the vector now? We need a parallel vector. But what we have is the parametric equation of a line M. If we look at the parametric equation of the line M, by only looking at the equation, we can get information, some information of that line. What we know is 2, negative 1 is a point on M. And we also know that 4, negative 1 is parallel, it's a vector parallel to M. That's what we know by only looking at the equation. Is that okay? It's like we are reversing the process that we carry out to get the equation. From if the point we put it here and the vector we put it here, if now we have the equation, we know what we are putting here is the point, what we are putting here is the parallel vector. That's the only thing that we are doing. Yes or no? So if this is M, we know that this vector 4, negative 1 is parallel to M. And what we know, what is the relationship between M and L? The relationship between M and L, the following. They are orthogonal. So this is L. So this vector 4 minus 1 is not parallel to L, so it's not the vector that we are looking for. This vector 4, negative 1 is orthogonal to L. So 4, negative 1 is orthogonal to L. So the vector that we need, let's say that the first component of that vector is A, the second component of that vector is B, is gonna be, is parallel to L. So if these two are parallel and this is orthogonal to L, any transversal, okay, forms the same angle with any two parallel things. So from these two, we can conclude that 4, minus 1 is orthogonal to the vector AB. That is the vector that we need. But if this is true, the dot product of these two vectors needs to be 0. Is that okay? Needs to be 0. This is telling us that 4 times A plus negative 1 times B, which is minus B, is equal to 0. So B needs to be equals to 4A. So this is telling us that now that any vector that is parallel to L is such that its second component is 4 times the first component. So the only thing that we need to do is to assign a value to A and to use this equation to get the corresponding value of B, and we are going to get one vector that is parallel to L. That is what we need. So if I use A equal 1, then B is going to be 4. Okay, this is just one vector. And now this information, all this information, L is orthogonal to the line M described by this parametric equation, was translated into the vector, a parallel vector. And now it's pretty easy. Now our complex exercise became a simple exercise because we have the point and the parallel vector. So the parametric equation of the line L in this case what is the point? 1, -2, and what is the vector? 1, 4. Is that okay? All right. So now we are in conditions to move forward and describe lines in R3. All right? What happens with a line R3? What happens if we want to describe a line in R3 using a parametric equation? So again, what we need is a point and one parallel vector, because that parallel vector is simply indicating what is the direction of that line. All right? With one point only, we cannot describe a line, because there are infinite lines passing across that point. But if we choose a point and a parallel direction, okay, well, we can say, well, out of all these infinite lines that are passing across this point, which one has the same direction as this vector? This one. That's the reason with one point and a parallel vector, we can describe a line. Okay? It's going to be the same, R3. Now we are in the three-dimensional space. And let's say that we have a line L. All right? And we know a point X0, Y0, Z0 now. And we have a vector A, B, C that is parallel to this line. Same thing now. If a point now X, Y, Z is on the line L, from the origin to this point X0, Y0, Z0, we have a vector with the same, whose components are the same as the coordinates of this point, and the same thing here. From the origin to these points X, Y, Z, we have a vector with exactly the same components, and we know that the subtraction of these two vectors is parallel to the segment of line connecting these 2 points, which in this case is that segment is a part of L, so obviously it's going to be parallel to L. Is that okay? So again, we have that X minus X0, Y minus Y0, Z minus Z0 is parallel to L. But ABC is also parallel to L. So if this is parallel to L and this is parallel to L, using transitivity, we can conclude that X minus X0 y minus y0, z minus z0 is parallel to A, B, C. Two vectors are parallel. Two vectors are parallel if we can find a scalar such that the first vector is equal to that scalar times the second. And pretty much this is leading us to a very similar equation. The only difference is that now we have one more component. All right? So x is going to be x minus x0 is equal to alpha times a, but I can take x0 to the other side, so x0 plus a alpha, y0 plus b alpha, and z0 plus c alpha with alpha real. And this is the parametric equation of the line. In R3. Okay, so pretty much the same thing. Well, again, we can have a very simple exercise. Find the parametric equation of the line that pass across the point 1 minus 2, 0, and is parallel to the vector -2 or 1. Oh, again, this is my point, so this is x0, y0, z0. This is my parallel vector, so this is A, this is B, and this is C. And my equation is going to be x equal to 1 minus 2 alpha, y equal to -2 plus 4 alpha, and z equal to 0 plus alpha. And we can use this equation for the same purposes we used the equation in R2. So we can give, if we have a point and we want to know if that point is on the line or not, the only thing that we need to do is to plug the value of x here, the value of y here, the value of z here, and verify whether there is one value of alpha making these three equations, converting these three equations into identities. Okay, satisfying all these equations simultaneously. All right, if we can find such an alpha, the answer is going to be yes for that given point. If we cannot find such an alpha, the answer is going to be no, that point is not on the line. Is that good? So, and the other point is, well, if we want to generate points on this line, we just need to assign values to alpha. We assign a first value to alpha, we use that same value for the three equations, and we are going to get the value for x, y, and z, which are the coordinates of the point that we are looking for. And we can repeat that process as many times as we want. So same thing. Is that okay? The one that is going to be a little bit more complicated now is the normal equation of the line. The normal equation of the line. Right? Normal equation of the line. All right. Look at the following. If we have a line now in R3, we have 3 dimensions here. I say, okay, before we use a point, again, one point we have infinite lines, and what we said in R2 was, what if I have an orthogonal vector? You say, well, what is the angle here? Is 90 degrees? No. What is the angle here? Is 90 degrees? No. What is the angle between these two? Well, they are parallel, and so on. So out of the infinite lines that we have, we are going to choose that one that is passing across that point by forming an angle of 90 degrees with the given vector. That's what we did in R2. What happens if I have an orthogonal vector now? So one orthogonal vector in R3, we cannot move the line this way. Because if I move the line this way, now the angle that this line is forming with my vector is not 90 anymore. You see? So it seems to be that this fits in my line. I cannot move it that way. It's determining my line somehow. But what happens if I move my line this way? Is that okay? So I'm going to keep this angle, 90, but I'm going to move my line this way. So it's 90 here. It's still 90 here with this vector. But it's not the same line, because I have one dimension that I can use it to escape. Is that okay? Let me do it with these markers for you to understand what I mean. I have my orthogonal vector here for this line. If I move my line this way, I'm changing the angle, so this vector is determining the line, is facing my line according to this direction. I cannot move it this way because I'm going to change the angle, so I cannot obtain another line passing across this point and move and forming an angle of 90 degrees if I do this. This line is not satisfying the conditions that I have anymore. But if I move it this way, this other line is still forming an angle of 90 degrees with the given vector and it's passing across my point. So only one orthogonal vector and one point in R3 do not suffice to determine a single line in R3. Why? Because I have a direction that I can use it to modify my line a little bit, so to get a different line satisfying the two conditions that I have. So how can I fix this? The way that I'm going to fix this is the following. What happens if instead of one orthogonal vector, I have two? Oh, now I can move my line to obtain another line satisfying the same condition. It's passing across the point. If I move it this way, I'm changing the angle with this vector. If I move it the way that I was moving before to obtain another example of a line satisfying my condition, I'm going to change the angle with this vector. If I move it in any other direction, I'm going to change maybe the angle with both vectors. Is that okay? So, what is this telling us? That for the normal equation of a line in R3, the information that we need is one point and two orthogonal vectors, two non-collinear orthogonal vectors. So 1 point and two non-parallel orthogonal. Let me put it this way. Two non-parallel vectors orthogonal to a line. So each of them is orthogonal to a line. Is that okay? So I have my line, I have my point, and I have a first orthogonal vector here, P, Q, W, or P1, Q1, W1, and another orthogonal vector here, P2, Q2, W2. Okay? So somewhere I have my origin here. If a new point X, Y, Z is coming, for that point to be on our line, the vector that these 2 points determine, that is the subtraction of these 2 vectors, X minus Z0, Y minus Y0, Z minus Z0 is parallel to the line. But P1, Q1, W1 is orthogonal to the line. P2, Q2, W2 is orthogonal to a line, which means that this vector, okay, is also orthogonal to X0, Y0, Z0, to the vector X minus X0, Y minus Y0, Z minus Z0, and also orthogonal, and also P2, Q2, W2 is also orthogonal to this. X minus Z0, Y minus Y0, Z minus Z0. Is that okay? And now, the only thing that we need to use is the criterion that we have for orthogonal vectors. If 2 vectors are orthogonal, the dot product needs to be 0. So the normal equation of the line is going to be what? P1 times X minus X0 plus Q1 times Y minus Y0 plus W1 times Z minus Z0 equal to 0. And from the second one, we're going to have P2 X minus Z0 plus Q2 Y minus Y0 plus W2 times Z minus Z0 needs to be 0. And this is the normal equation of the line R3. And I'm using a little bit because I have 2 equations. So it's basically the normal equation is going to be a system of equations for the line R3. Is that okay? Again, a very simple exercise. One of those, very simple, is going to be exercise, find the normal equation. I'm going to continue abusing of the language a little bit of the line passing across the point 1 to 1 and orthogonal to the vectors, to each of the vectors let's say 2, -1, 3 and 2, 0, 3. Okay? So the only thing that we need to do is my point, this is X0, this is Y0, this is Z0, and this is my first orthogonal vector. So this is P1, this is Q1, this is W1, this is P2, this is Q2, and this is W2. I go here and I say, what is going to be the solution in this case? P1 is 2 times X. X0 is 1, so minus 1. Q1 is -1, so minus Y minus Y0 is 2. Okay, plus W1 is 3, Z minus and Z0 is 1, equal to 0. Okay, and now P2 is 2, so 2x minus x0, so same thing, plus 0, y minus y0, so that goes away. Again, plus 3, z minus z0. And this here is the normal equation of the line in that case. Is that okay? All right, good. Good. So what I'm gonna do now is I will talk about the parametric equation of a plane and the normal equation of a plane in R3, and at the end we are gonna do a couple of exercises combining everything. All right? Okay. What about a plane? Well, a plane is a bidimensional object. If I want to describe a plane, what we are doing with parametric equations? So parametric equation, basically what we're using is a point and vectors that are parallel to the object that we are describing. In this case, the object is a plane. So basically, a plane is gonna have an orthogonal vector and two parallel vectors. Okay, and two parallel vectors. Well, let's say that if we have a plane, the vectors are in the origin. It's a vector that I take it and it's going to be parallel to the plane. If I take it and I translate it parallelly, that vector is going to fall within the plane, inside the plane. So okay, that's a parallel vector. Or what we can say is also that any parallel vector is going to be orthogonal to the normal vector to the plane, or orthogonal vector to the plane. Is that okay? So again, this is telling us if we want to describe a plane using a parametric equation, what we need is one point and two non-parallel vectors. Non-parallel is saying that these two vectors are not parallel. They are not parallel, but both are parallel to the plane. Okay? Let me explain a little bit what is the intuition behind that equation. So let's suppose that the plane that I want to describe is the board. So I have a point and I have two parallel vectors. What is going to happen here if I want to describe any other point on this plane? So what we can do is the following. Remember what is the interpretation of the addition of two vectors. The addition of two vectors is going to be the principal diagonal of the parallelogram that we confirm using each vector as a side of that parallelogram. So look at the following. What happens if from this point I start moving parallel to this vector? Let me call this vector y. I'm going to start moving parallel to y until I reach the direction, the line that this vector is generating, the line that this vector is determining. When I reach that line, I'm going to get a point in this line. This given point and this new point are determining a vector that is parallel. Let me call this vector x, that is parallel to x. So this pink vector now, okay, is going to be some alpha times x. Is that okay? Some alpha times x. And I can repeat this process. What happens if I start now moving parallel to x? Let's suppose that this is parallel until I reach the line that y generates. I'm going to get a point here. What is happening? That these 2 points now are determining a vector that is parallel to y. So I can get this green vector multiplying y by some scalar. Let me call it beta. Is that okay? Is that okay? So if I add these two vectors, I'm gonna get that point. And I can repeat that for any point. I move parallel to y until I reach this line. I move parallel to x until I reach this line. The two vectors that I'm obtaining here, one is parallel to x, the other is parallel to y. So this is an scalar times x, this is another scalar times y. And if I add, I'm gonna get this point. I can do that for any point. Yes or no? Is that okay? Is that good? All right. So what is this telling us? What is this telling us? If this is at 0, y0, z0, what this is telling us is this vector here is what? Well, this vector here is alpha times x. This vector here is beta times y. And what I notice that if I add these two, I'm gonna get this vector here. But what is this vector here? If this is the point x, y, z, this vector here is x minus x0, y minus y0, comma z minus z0. And what this is telling us is that the parametric equation of the plane is x equals to x0 plus alpha times the first component of x. So I will use a1, b1, c1. So a1 times alpha. I will use y as a2, b2, c2. So plus a2 times beta, and that for all the components. Y is equal to y0 plus b1 times alpha plus b2 times beta, and z is equal to z0 plus c1 times alpha plus c2 times beta. And this is the parametric equation of a plane in R3. Is that okay? So again, we are going to have an easy exercise. Find the parametric equation of the plane passing across the point 2, 0, 0 and parallel to each of the vectors 2, 1, 1 and 3, negative 3, 0. Okay? But this again is pretty simple because this is gonna be x0, y0, z0. This is a1, b1, c1, and this is a2, b2, c2. Oh, I go here to my generic equation and I plug every specific value into the corresponding symbol. So what is x0? 2, y0 is 0, z0 is also 0, so I won't write that. Plus, what is a1? What is a1? a1 is gonna be 2, so 2 times alpha, and a2 is gonna be 3, so plus 3 times beta. Okay? What is gonna be b1? b1 is 1, so alpha here. And b2 is negative 3, so minus 3 beta. And c1 is 1, so alpha here, and C2 is 0, so that's it. Alpha and beta are now real numbers. Okay, so this is pretty easy. All right. Okay, what happens if we want to describe a plane now using a normal equation? Again, what is the pattern here? For a normal equation, what we use is a point and vectors that are orthogonal to the object that we are describing. In this case, the object that we're describing is a plane. How many vectors in R3 we need to describe a plane? How many orthogonal vectors we need to describe a plane through a normal equation? One vector, because a plane is bidimensional. We are in a three-dimensional space. We have only one direction orthogonal to that plane. Is that okay? All right. Now let's see what is the equation. The normal equation of a plane. Okay. Well, we have the origin somewhere. We are trying to describe this plane. We know a point at 0, y0, z0. And we have a vector that is orthogonal to our plane. Let me call it P, Q, W. All right. And if a point x, y, z is coming and that point is on the plane, well, this point is determining this vector here. This other point is determining this vector here, and we know that the subtraction is, we can put it here. We can, it's a vector that is parallel to the segment of line connecting these 2 points, and the magnitude is exactly the distance between these 2 points. Is that okay? Oh, but if these 2 points are on the line, that vector is, sorry, if these 2 points are on the plane, this vector is parallel to the plane, and so what we have is that at 0, y0, z0, sorry, x minus z0, y minus y0, z minus z0 is parallel to a plane at the vector p, q, w is orthogonal to the plane. So these two are orthogonal as well. So PQW, the vector P, Q, W is orthogonal to the vector x minus z0, y minus y0, z minus z0. And again, what do we know about orthogonal vectors? That the dot product is 0. So what we are going to have? That P times x minus z0 plus Q times y minus y0 plus W times z minus z0 is equal to 0. And this here is the normal equation of the plane. Okay, very easy exercise. Well, find the normal equation of the plane passing across the point to 1, 3 and orthogonal to the vector y, negative 1, 3. So, very simple in this case. This is x0, this is y0, and this is z0, and this is p, q, and w. So we are going to have that 1 times x minus x0, that is 2, minus 1, that is q, times y minus y0, that is 1, plus w, that is 3, times z minus z0, that is 3, is equal to 0. And this is going to be basically the normal equation of the plane in this case, which obviously we can rewrite as x minus y plus 3z minus 2 plus 1 is minus 1 minus 9 minus 10 equal to 0. All right? So these are the very easy exercises that we can solve. Let me give you a summary of the equations that we have for lines and plane, and then we are going to solve a little bit more complex exercise involving lines and planes. Is that good? All right. Okay. So when we put line, plane, parametric equation, normal equation, and what we have for the line. 1 point at 0, y0, z0, 1 vector parallel to the line, let's say A, B, C. And the parametric equation is going to be x, y, z equals to x0, y0, z0, x0 plus A times alpha, y equal y0 plus B times alpha, z equals z0 plus z times alpha. Alpha is a parameter. Is that okay? All right. So something that we can notice is the following. The number of parameters that we're going to have in a parametric equation is the same as the dimension of the object that we are describing. A line is a one-dimensional object, so we use only one parameter. So the parametric equation of a plane is pretty similar. And what we need? 1 point x0, y0, z0, and 2 vectors parallel to the plane. Let's see, A1, B1, C1, A2, B2, C2, and the vectors themselves are not parallel. Is that okay? So each of them is parallel to a plane, but they are non-parallel if we compare them. And the parametric equation is going to be x equals to x0 plus a1 alpha plus a2 beta, y is equal to y0 plus b1 alpha plus b2 beta, and z is equal to z0 plus c1 alpha plus c2 beta. Now alpha and beta are parameters here, are real, are scalars. Is that okay? So notice that now a plane is a bidimensional object, and we are using 2 independent parameters here to describe them, to describe that plane. Is that okay? So again, as a general idea, is the number of parameters that we are using or the number of parallel vectors that we need is equal to the dimension of the object that we are describing. Is that okay? And what is going to be the normal equation for a line R3? So what we need, 1 point, say x0, y0, z0, and 2 vectors orthogonal to a line let's say P1, Q1, W1, and P2, Q2, W2, but if we again compare these two vectors, they are non-parallel. Is that okay? And the normal equation of the line is gonna be P1 x minus x0 plus Q1 y minus y0 plus W1 z minus z0 equal to 0. And the second is P2 x minus x0 plus Q2 y minus y0 plus W2 z minus z0 equal to 0. Is that okay? All right. For a plane, what we need is 1 point and 1 vector orthogonal to a plane. Let's say that the point is z0, y0, z0, and the point is PQW. All right? And the equation is going to be P times x minus x0 plus Q times y minus y0 plus W times z minus z0 equal to 0. And now notice that is the opposite. How many orthogonal vectors we need? Well, a line is one-dimensional, but we have the line in three-dimensional space. So from 1 to 3, how many dimensions we need to complete the 3? 2. That's the number of vectors. Notice that since we are using orthogonal information, is that information is not from inside. That information is from outside. So it's not the dimension of the line itself, like in the case of the parametric equation, is what we need now to complete the dimensions of the ambient space. This line is a one-dimensional object. To complete a three-dimensional object, we need 2 more independent directions, 2 more dimensions. Is that okay? And the plane is the opposite. The plane itself is a bidimensional object. And we have that plane inside a 3-dimensional object. How many directions we need from 2 to complete the 3 that we have in the ambient space? Only 1. Is that okay? So again, the number of parameters or the number of parallel vectors is the same as the dimension of the object that we are describing. The number of orthogonal vectors that we need for the normal equation is not the dimension. It's what we need to complete from the dimension of the object that we are describing, the dimension of the ambient space, that in this case is R3. But in both cases, notice that 1 parallel vector plus 2 orthogonal vectors give us 3. 2 parallel vectors plus 1 orthogonal vector, 3. So the number of parallel vectors that we need plus the number of orthogonal vectors that we need give us the dimension of the whole space in any case. Those are rules that we are gonna be repeating constantly here, because this is something that is not only valid in R3, this is gonna be valid in any Rn when we were describing linear spaces that are generalizations of this one. Is that okay? All right. So let me finish this with a little bit more complex exercise. So exercise, just to give you an idea. find the parametric equation of the plane let me give a name to this plane. I'm going to call it pi. If you know, first, pi is parallel to the line r described by the equation -3, 2 plus alpha, comma, 1 plus alpha, alpha real. Okay? Also, pi is orthogonal to the plane, I'm gonna call it rho, described by the equation it's -2y plus z equal 8. Okay? And pi pass across the intersection point of the line is described by minus alpha 2 plus alpha minus 5 plus alpha, and the plane theta described by the equation minus 2x plus y equals 2. Okay, so again, this is telling us that we need a parametric equation of this plane. Parametric equation of this plane, we need a point and two vectors that are parallel to a plane but themselves are non-parallel. Okay, and well, that information is not explicitly given here. Okay, what can we do now? Well, we need to use this information somehow to get what we need. And if we look at the parametric equation of this line R, and what we know is the following. I'm going to erase this part a bit. Well, we know that we have the plane and R is parallel to my plane. But the equation that I have describing R is a parametric one. So by only looking at this equation, what I know? By only looking at this equation, what I know? Look at the parametric equation of the line. The constants here are a point, and the coefficients of alpha are a vector parallel to a line. So by only looking at this equation, I can say, oh, -3, 2, 1 is a point on R. And in addition, 0, because I don't have alpha, so 0, 1, 1 is a vector parallel to R. So 0, 1, 1 is a vector parallel to R, but R is parallel to my plane pi, so this vector is parallel to the plane. So I have one of the two vectors that I need to describe my plane. 0, 1, 1 is also parallel to pi, so I have one vector parallel to pi here. Yes or no? Okay, good. What else I know? Oh, what the other thing that I have is I have a plane rho now, and what I know is that rho is orthogonal to pi. Rho is orthogonal to pi. So if rho is orthogonal to pi, any vector that is orthogonal to rho is going to be parallel to pi. Yes or no? And what is the equation that I'm using to describe rho? A normal equation. What do I know? What do I know about a normal equation? Look at the normal equation of a plane. What do you think that is going to be the coefficient for x, the coefficient for y, and the coefficient for z? The coefficient for x is going to be p, the coefficient for y is going to be q, the coefficient for z is going to be w. But p, q, w are the components of a vector that is orthogonal to the plane. What I know here, that 1 minus 2, 1 comma minus 2 comma 1 is orthogonal to rho, but rho is orthogonal to pi, which implies that 1 minus 2 comma 1 is parallel to pi. Is that okay? So I have a second vector. I have a second vector parallel to pi. I have the two vectors that I need. These two vectors are non-parallel. Okay? So I have the two vectors that I need. What is the only thing that I'm missing? What I'm missing is my point. But here I have information about a point because I know that pi is passing across this intersection point. I don't have that point explicitly, but I can find it. It's not too hard to find that point. Okay. If you look at this parametric equation of S, that means that the first component of the points is described by negative alpha. The second components for those points in the line, on the line S, are described by 2 plus alpha, and the third component of those points on S are described by the formula minus 5 plus alpha. And any point on the plane, the first minus twice the first component plus the second component needs to be 2. But if a point is in both, because it's an intersection point, those points needs to be generated by these formulas. The coordinates of those points are generated by this formula. At the same time, the points are satisfying this. Oh, what I'm going to do? If x needs to be this, y needs to be this, and z needs to be this, to be on the line, and the same x needs to, and the same y and the same z need to satisfy this equation, if the point is on the plane, that points that are in the intersection need to satisfy both. So what I'm going to do is, x is this, but x is here. So I'm going to write minus 2x plus y is equal to, needs to be satisfied to be on the plane, but x is minus alpha, so minus 2 times minus alpha plus y is 2 plus alpha. 2 plus alpha, we don't have z here, so this is equal to. And this is telling us that 2 alpha plus 2 plus alpha needs to be equal to 3 alpha plus 2 is equal to, this cancel out with this, 3 is alpha is 0, alpha is 0. Again, this is not the point. This is the value that I need to assign to the parameter alpha here to get the point that I need. If I put alpha here, the point is going to be 0, 2, minus 5. And I have the two vectors that I need and the point that I need. I just need to go here and to plug those values. If I plug those values here, in this case, the parametric equation of my plane is gonna be, what is x? 0. What is x 0? 0. What is y 0? 2. What is z 0? Minus 5. What is a 1? Oh, we showed you one. I'm gonna choose this one. 0. What is a 2? 1. So beta. X is just beta. What is a b1? 1. So plus alpha. What is b2? Sorry, here, minus 2 beta. What is c1? 1. I have my beta already here. Oh, no, c1, sorry, 1. No, here. Alpha. And what is my c2? Here, beta. No, alpha and beta. And that's the parametric equation of my plane in this case, and this exercise if solved. Okay? So, thank you very much. That's going to be all for today.